A right circular solid cylinder floats at rest in water with its axis vertical. The radius of the cylinder is 5 centimeters and its height is 12 centimeters. So we get these values in meters. The radius is 0.05 meters, the height is 0.12 meters. 95% of the cylinder lies below the surface of the water. We want to find the weight of the cylinder. Let's look at the forces acting on the cylinder. Well, we have its weight vertically down, that's what we have to determine. Now this is not the only force acting on the cylinder, because the cylinder is not accelerating, it's in equilibrium. So by Newton's second law, F equals ma, F equals m times 0, which is 0. The resultant force on the cylinder is 0. All the horizontal forces cancel to 0. So there's an upwards force on the cylinder. It's the contact force of the water on the cylinder, also known as the buoyancy force. It acts vertically upward, as we've seen before. We know by Archimedes' principle that the buoyancy force acting on the cylinder is the weight of water displaced by the cylinder. Now we know that W must equal the magnitude of the buoyancy force, because the resultant force on the cylinder is 0. So we have the law of flotation. The weight of the floating object is equal to the weight of the water displaced by the floating object. Okay, to get the weight of the cylinder, we need the mass of the cylinder, which I'm writing as mc, times g. To get the buoyancy force, which is the weight of the water displaced for a floating object, we have to get the mass of the water displaced as mw times g. So you can see that the g's cancel from both sides. To get the mass of the cylinder, we can use the volume of the cylinder, because we can actually calculate the volume. We have the dimensions of this cylinder. But we need to multiply the density of the cylinder, rho c, by the volume of the cylinder. The density of the cylinder is what we don't know. However, on the right hand side we need the mass of water displaced. That's the density of the water displaced times the volume of the water displaced. Now we do know the density of water displaced. The density of water is 1000 kilograms per meter cubed. As for the volume of water displaced, we can calculate that also. The volume of water displaced is equal to the volume of the part of the cylinder that's immersed. Okay, we're given that 95% of the cylinder is immersed. So the cylinder has pushed out the water. It has displaced the water, and the amount of water displaced, of course, is equal to the part of the cylinder, the volume of the immersed part of the cylinder. Okay, so let's work with this here. Let's get the volume of the cylinder. Well, let's just pi times the radius squared times the height. The cross-sectional area is the area of a circle, pi r squared, and we multiply by the height. Okay, and now we get the density of water on the right hand side, that's 1000, times the volume of water displaced. Okay, so we want the volume of 95% of the cylinder. Well, that's just 95% of this quantity here. Notice something interesting in this equation. Notice that we don't need the radius or the height of the cylinder, because we can divide both sides. Okay, see, they cancel out. So I could have just written r squared h here. You know, if we didn't know the radius or the height, it wouldn't make any difference. What we do need to know is that 95% of the cylinder is immersed. This number 0.95 appears on the right hand side. Okay, so we're getting 95% of the volume of the cylinder to get the volume of the immersed part of the cylinder, which is equal to the volume of the water displaced by the cylinder. So we see that the density of the cylinder is 1000 times 0.95, which is 950 kilograms per meter cubed. Notice that we could have arrived at this figure by getting 95% of the density of water. Okay, so the density of the cylinder is 95% of the density of water. So if we have an object that's immersed in water, and we know what percentage of it is immersed, well, the percentage volume of it that's immersed, so 95% of the volume of the cylinder is immersed in water, then we know that the density of the object must be that percentage of the density of water. So if 95% of the volume is immersed, then the density of the object is 95% of the density of water, which is 950 kilograms. So the dimensions we don't need to worry about the radius and the height. It's the percentage of the object that's immersed in water that counts. Now at last we can get the weight of the cylinder. We need the mass of the cylinder times g. The density is 950. Now we need the volume. So this time we do need the dimensions. Okay, the volume is pi r squared h. If we use g equals 9.81, our answer is 8.78 newton. A solid sphere has a radius of 2 centimeters. The relative density of the sphere is 0.7 and it is completely immersed in a liquid of relative density 1.2. The sphere is held at rest by a light inelastic vertical string which is attached to the base of the tank. We are going to find the tension in the string. So let's look at the forces on this sphere. Well, we have its weight W acting vertically down. I've put its tail up here. The tail can be anywhere, of course. Now, the sphere is attached to this string. The string exerts a force on the sphere in a direction along the string and away from the sphere. Okay, so this is a contact force. Actually, I'll try and make these vectors look a bit more realistic. I'll just shorten W for now. T might look like this. Now, these are not the only two forces acting on this sphere, of course. The sphere is in equilibrium, its acceleration is 0. So there must be a force acting upwards whose magnitude is the sum of the magnitudes of these two forces. That force is the buoyancy force. We call it B. It's the force on the sphere due to the liquid. Okay, let's get W, the weight of the sphere. Ultimately we want T, the force on the sphere due to the string, which is the tension in the string. Right. The weight of the sphere is the mass of the sphere times g. What's the mass of the sphere? It's the density of the sphere times the volume of the sphere. The density of the sphere is got from the relative density, which is 0.7. We multiply that by 1000 to get 700. The volume of a sphere is 4/3 pi r cubed, where the radius is 2 centimeters. That's 0.02 meters. To 2 decimal places we get 0.23 newtons. Now I've used 9.81 for g, but sometimes 10 is used. 10 is an approximation to 9.81, not a very good one, but you know, whatever. I prefer to use 9.81. Now let's get B, the magnitude of the buoyancy force. We use Archimedes' principle, which tells us that the magnitude of the buoyancy force is the weight of liquid displaced by the immersed object. So the weight of the liquid displaced is the mass of the liquid displaced times g. What's the mass of the liquid displaced? Well, it's the density of the liquid displaced times the volume of the liquid displaced. What's the density of the liquid displaced? Well, the relative density of the liquid is 1.2, so the density of the liquid is 1.2 times 1000, which is 1200. What's the volume of the liquid displaced? Well, that's equal to the volume of the immersed object, which is the sphere. Okay, so the sphere takes the place of the liquid. The volume of the sphere is 4/3 pi r cubed. Okay, to 4 decimal places we see that B is 0.3944. So now we can go and find out what T is. As we've said before, A is 0, so by Newton's second law the resultant force is 0. So the sum of the vectors pointing down equals the sum of the vectors pointing up. So the sum of the magnitudes of the vectors pointing down is T plus W, and that must equal B. B is the only vector pointing up. So you can see now that these vectors are drawn to scale. If you add this vector onto this vector, you get a vector that looks like this one here but pointing up. So how do we find T? Well, we take vector B and subtract W. To 3 decimal places you get 0.164 newtons. Now you can see that this picture makes sense. The buoyancy force, 0.3944, is greater than the weight of the sphere. So if the sphere wasn't attached to the base of this tank, then the sphere would just float upwards. A solid piece of metal has a weight of 26 newtons. When it is completely immersed in water, the metal weighs 21 newtons. We want to find the volume of the metal. Now, before we answer this problem, I just want to explain the reading on the spring balance. I want to show where that comes from. Well, it's the force on the spring balance S due to the metal M. And it's in a downward direction, of course. We can apply Newton's third law to find the force on the metal due to the spring balance. So there must be an equal but opposite force on the metal due to the spring balance. We'll call this force FMS. Here's the reminder of Newton's third law. The force on S due to M is minus the force on M due to S, which means that these vectors have the same magnitude but opposite directions. So, the origin of the reading on the spring balance is the force on the metal due to the spring balance. Now this is important. Now, let's get the resultant force on this metal. Well, actually we know the resultant force is zero, because the metal is sitting here in equilibrium. Its acceleration is zero, so by Newton's second law, F equals ma, the resultant force F is zero. What's the other force acting on it? Well, we obviously have its weight, which is vertically down. Let's call it W. Since F is zero, the sum of the forces on this object must be zero. So these are the two forces acting on it, the only two forces acting on it. So we can see straight away that W must have magnitude 26 newtons. So we see that the reading on the spring balance gives us the actual weight of the object, provided that the object is weighed in air or weighed in a vacuum. Well, if it's weighed in air, there's going to be a little tiny buoyancy force on it due to the air, but that's so small that we can ignore it. So weighing an object in air is virtually the same as weighing it in a vacuum. So the reading on the spring balance will actually give us the weight of the object. Notice here that weight is measured in newtons because weight is a force, but in everyday life people refer to the weight as so many kilograms or whatever. It's actually the mass that's in kilograms. So this is quite misleading, of course, because weight is a different unit in scientific usage than it does in everyday usage. Now, the object is immersed in water and the water level rises. So this point here is the level before immersion. So the water rises to a new level. And the water that's displaced or pushed out by this object must equal the volume of the object. Let's look at the forces acting on the object when it's immersed in the water. Well, we have its weight vertically down. Now that never changes. It's the force on the object due to gravity. It's 26 newtons. So even though we say that the object weighs less in water, see the reading here is less than the reading here, the actual weight never changes, of course. Gravity doesn't change when we put an object into water. The earth pulls on the object with the same force whether it's in water or not in water. Gravity always pulls with the same force on an object. Now we said that the reading here is the force on the metal due to the spring. So it's 21 newtons. Now these can't be the only two forces acting on this object because its acceleration is zero. So by Newton's second law, the force on it is zero. If these were the only two forces acting on the object, then the object would accelerate downwards. The resultant force would be 26 minus 21, which is 5 newtons downwards. So there must be a force of magnitude 5 newtons acting upwards. This force is the force on the object due to the surrounding water. The water pushes up on it. This is called the buoyancy force, and its magnitude here is 5 newtons. 5 plus 21 is equal to 26. So now the object is in equilibrium. Now we can apply Archimedes' principle. Archimedes' principle says that the buoyancy force B is equal to the weight of the liquid displaced. So in this case the liquid is water. Okay, so what's the weight of the water displaced? Well, it's the mass of the water displaced, which we will call m, times g. But what is the mass of the water displaced? Well, the mass of water is the density of the water times the volume of the water that's displaced. So m equals rho times v. What is the density of water? Well, we know that it's 1,000 kilograms per cubic meter. The volume is what we're after, and we have to multiply that by g. So the only thing that's missing in this equation is v. Okay, so we multiply 1,000 by 9.81. That's the acceleration due to gravity, to get 9,810. So we divide 5 by 9810. That gives us 0.0005 meters cubed. Now, as an aside, I'll briefly mention units. Okay, the units of density are kilograms per meter cubed, and that's multiplied by the units of acceleration, which is meters per second squared. Now, we have 5 newtons. Well, the newton has units of kilograms meters per second squared. It's mass times acceleration. The unit of mass is the kilogram. The unit of acceleration is meters per second squared. So you can see that these cancel above and below the line. The kilograms also cancel. So we have 9810 divided by m to the power of 3, and we can bring that up. Well, actually, we can multiply above and below by m to the power of 3 if you like. Cancels underneath, and our final unit is meters cubed, as expected. It's the unit of volume. So this is the volume of the water displaced, okay? But the volume of the water displaced is just equal to the volume of the object. So this is the answer to part 1. In part 2, we want the relative density of the metal. So we will start by getting the density of the metal. We know that the weight of the metal is 26 newtons. That's equal to the mass of the metal times g. So let's get the mass of the metal. The mass is 26 newtons divided by g, which is 9.81. To 2 decimal places, we get 2.65 kilograms. The density of the metal, or the average density of the metal, if its density isn't uniform, is the mass of the metal, 2.65 kilograms, divided by the volume of the metal, 0.0005 meters cubed. So, on average, each meter cubed of the metal has a mass of 5,300 kilograms. You know, if the density is uniform, every meter cubed has exactly 5,300 kilograms. If the density is not uniform, well, this is just an average for each kilogram. Now, the relative density of a substance is the density of the substance relative to water. So we divide the density of the metal by the density of water, which is 1,000 kilograms per meter cubed. These units cancel out, so relative density is dimensionless. So we can say that the density of this metal is 5.3 times the density of water. A right circular solid cylinder has a base of radius 8 cm and a height of 18 cm. The relative density of the cylinder is 3, and it is completely immersed in a tank of liquid of relative density 0.9. So to get the density of the tank, we multiply its relative density, which is 3, by the density of water, which is 1,000. So we get 3,000 kilograms per meter cubed, because the relative density is the density of the tank compared to water. The tank is 3 times more dense than water. The liquid is 0.9 times as dense as water, so we multiply 0.9 by 1,000 to get 900 kilograms per meter cubed. The cylinder is held at rest by a light, inextensible vertical string which is attached to a fixed point P. The upper surface of the cylinder is horizontal. We want to find the tension in the string. Let's get the forces acting on the cylinder. Well, the string exerts an upward force on the cylinder. We will call the magnitude of this force T. Now this is what we're after. Now we have the weight of the cylinder. So how do we calculate that? Well, the weight is the mass of the cylinder times g. To get the mass of the cylinder, we have to multiply its density by its volume. So what's the density of the tank? Well, we just have it here as 3,000. What's its volume? Well, it's in the shape of a cylinder. The volume of a cylinder is the cross-sectional area, which is a circle of radius 0.08, and this has to be multiplied by the height, which is 0.18, and then we have mass times g. Okay, using 9.81 for g to 2 decimal places, we see that the weight of the tank is 106.51 newtons. Now there's another force acting on the tank, because the liquid is in contact with the tank and the liquid exerts a force on the tank. As an aside, we will take a closer look at the force on the tank due to the liquid. Let's take the base of the tank. The base of the tank is horizontal, so all points on the base of the tank are at the same depth below the surface. So the magnitude of all the forces at points on the base of the tank are equal, and they're all pointing vertically up. They're all pointing perpendicular to the surface that they're in contact with. So they're in contact with the liquid that's in contact with the base of the tank exerts a force perpendicular to the base. That means vertically up. And all these vectors have the same magnitude. I'll just show them a little bit bigger. Okay, so we can imagine summing all these vectors to get the resultant. They're all pointing in the same direction, so it's quite easy to sum them. Now, what about forces on the sides of the tank? Well, the force varies linearly with depth. Actually, look more like this. The force at this point would have the same magnitude as the force on the base, because this point is the same depth below the surface of the water. But as we go up along the tank, the magnitude decreases linearly until we get to the top, where the magnitude is lowest. But we have the same forces acting all around the tank, so they all just cancel each other out, all these forces. The forces acting on the side of the tank are all horizontal forces, because they're perpendicular to the curved surface of the tank. And if a force is perpendicular to the curved surface of the tank, it has to be horizontal, because the curved surface is vertical. Okay, so contact forces are perpendicular to the surface. Now, what about the top of the tank? If we take a point on the top of the tank, there is a contact force acting down the way. Okay, so the force is acting at this point here. I put the tail of the vector at this point, but it doesn't matter. I could have put the head at the point. So it's perpendicular to the surface of contact of the liquid with the tank. So that means vertically down in this case. So we have all these forces acting down, and if we sum all them, we will get one resultant force on the top face of the tank. But its magnitude will be less than the magnitude of the force on the bottom face of the tank. Okay, so all these vectors up here have smaller magnitude, because the depth at the top of the tank is less than the depth of the bottom of the tank. So anyway, if we sum all the vectors, all those force vectors, we'll get one vector pointing vertically up, and that's the buoyancy force. It's got no horizontal component, of course. So these are the three forces acting on the tank, and they must sum to zero, because the acceleration of the tank is zero. So by Newton's second law, the resultant force on the tank is mass times zero, which is zero. So the sum of the upwards vectors must equal the downward vector w. If we sum the magnitudes of b and t, we must get vector w. We are after t, so we need to know what b is. So here is where we apply Archimedes' principle. We know that the buoyancy force on an object is the weight of the liquid displaced by the object. So how do we get that? The weight of the liquid displaced is the mass of the liquid displaced, m times g. That's the weight. What's the mass of the liquid displaced? Well, it's the density of the liquid displaced times the volume of the liquid displaced. Okay, so that's the mass. So what's the density of the liquid? It's 900. What's the volume of liquid displaced? Well, that's just the volume of this cylinder, and we actually calculated that in here. So we just copy that, and we have to multiply this by g. If you work this all out to 2 decimal places, you get 31.95 newtons. Okay, so if we go back to our diagram, we have a force of 106.51 newtons acting vertically down. We have a force of 31.95 newtons vertically up, and we have to find out what t is. So obviously if we add the magnitudes of these two vectors, we must get 106.51. we get an answer that's very close to 75 newtons.